Vectors are the language of physics. Represented by an arrow, the vector v has a magnitude or a length and a direction given by an angle theta. Notationally, a vector may be written with an arrow over it or in a boldface capital letter. Suppose I want to add two vectors a and b together. Geometrically speaking, we would add these two vectors head to tail. The resulting vector from start of A to the finish of B would be the vector C, representing the sum of the two vectors. Now, to find the magnitude of a vector, we must use the notation absolute value of A, or A that is not bold-faced. In order to find a direction angle, you have to employ a little trigonometry. The right triangle formed here gives us vector components as the adjacent and opposite sides of this right triangle. The cosine being the adjacent over the hypotenuse, or the v1 component over the magnitude, requires us to use the magnitude formula for vectors for its denominator. Then, employing the inverse cosine, we can find this angle in reference to where it lies from the x-axis. Now, consider this vector v, 3, 4, and let's say we want to find its magnitude. We use the formula for vector magnitude, which is really the Pythagorean theorem, and we get 5. It's a 3, 4, 5 right triangle. To calculate the angle, we take the adjacent over hypotenuse 3/5. The inverse cosine of this 3/5 will give us an angle here, roughly 53.1 degrees. Now, a vector pointing in the opposite direction gets associated with a negative sign, algebraically speaking. Vector addition is commutative. That means that we can add it out of order and still get the same answer. Geometrically, if we take A first, then B, add them head to tail, we get a third vector, let's call it C, and we would see that we would get this exact same vector if we added the two vectors A and B, B first, then A. Both result in the same vector. Now, this is often associated with something called a parallelogram rule for vectors. The diagonal is the sum. Subtraction is just simply adding a negative vector, so the same rules would apply like you would see in algebra. Although, geometrically speaking, this vector b with a negative sign would now point in the opposite direction. Adding it head to tail would give us the difference. Now, there's a couple of different multiplications with vectors, starting with scalar multiplication, multiplication of a vector with a number. So if c is a scalar, c times that vector would represent a dilation of that vector, a stretching or shrinking of that vector. Scalar multiplication does not change the direction angle. A couple of properties of algebra that we would see with vectors. Well, first, we already saw that vector addition is commutative. So now, what about the distributive property combining scalar multiplication and addition? And it works just as you would think. You distribute the scalar to each vector, and then you can add the two resulting vectors. The associativity of vectors, well, yeah, the grouping works as well. Now, vector multiplication, the product of two vectors, or the dot product, or inner product as it's called, is very important, especially in physics. The dot product of a vector with itself would be its square magnitude. It's the sum of the square of the components. So the dot product is a scalar value. The dot product can also be written in the formula form a dot b is equal to the magnitude of a, the magnitude of b, multiplied by the cosine of the angle between those two vectors. Again, this is for two different vectors being multiplied together. The inner product of two vectors, technically speaking, could be stated as B multiplied by the scalar projection of A onto B. A quick review. So let's say we have two vectors with their components A1, A2, B1, B2, magnitudes found in the natural way we've discussed before, and angles found in the way that we discussed before. Scalar multiplication has a number times a vector, where the dot product is the product of two vectors, giving us a scalar value. There's a component formula for dot product, and there's a trigonometric formula for the dot product. A few more odds and ends. The dot product is distributive. If two vectors A and B are perpendicular to each other, that is, that they form a right angle between each other, then the cosine of that angle would be 0, and their dot product therefore would also be 0. So if the dot product of two vectors is 0, they are perpendicular to each other. If they're parallel, that means they're going to be going in the same direction. Their angle would be 0. The cosine of that angle, 0, would be equal to 1. And so if two vectors are parallel, we see that they're just the product of the scalar values of their magnitudes. An interesting feature. If we were to let a vector C be the difference of two vectors, and then we wanted to multiply C with itself through a dot product, we obtain something familiar. Through a little distribution here, double distribution, and a few dot product rules applied, we get the famous law of cosines that you might remember from high school trigonometry. The cross product is a different or third type of multiplication between two vectors. So if A and B are two vectors, there's a trigonometric formula that defines a new vector along the normal vector direction, which is perpendicular to the plane in which the two vectors A and B would live. If A and B live on the xy plane, then a vector perpendicular to that one, call it n for normal, would be pointing in the third dimension z, perpendicular to both those vectors. A unit normal with the little hat notation has a length of 1, and so a times b times the sine of this unit normal vector would give us a magnitude multiplied by this normal vector. So a vector pointing in that direction of a given magnitude. The cross product is also distributive, and so we can define vectors in a perpendicular dimension by doing this cross product. Vectors in component form, v1, v2 being the components, again form a right triangle with the angle theta, and in unit vector form, v1 times I plus v2 times j, where I and j are your unit vectors or your basis vectors that live along the axes of the given dimensions. They have unit length. So the components are just scalar multiples of these unit vectors, a linear combination of those. The components are the size of the vector, and the basis vectors give us something in terms of direction. Three-dimensional vectors extend in the natural way with a third dimension z, a third unit vector or basis vector k, so then that gives us ijk, or in linear algebra terms, e1, e2, and e3. Again, the components give us the size of the vector, whereas the unit basis vectors give us some information about direction. So a vector v is a linear combination of these three things: v1 in the I direction, v2 in the j direction, and v3 in the k direction. A linear combination giving us the vector v. So we see that the main players for vectors are these two parts, the components and the basis vectors. This becomes important for higher level algebra when dealing with something called a tensor. A few more interesting features. The cross product, A cross B, is also the determinant of the matrix formed by the row with the unit basis vectors and the components of the two vectors. A determinant is a number obtained through multiplying the rows and columns of a matrix together in a certain way. So you can see this sort of crisscross pattern as I'm moving through here. If I want to go in the J direction, I cross off the J row and the J column and use the numbers that are not in that highlighted in blue. So this is just quickly going through the determinant of a matrix, something you would learn in linear algebra, and I'm not going to go into too much depth here. But each of these times we're getting a scalar component in the unit directions, and that's going to give us a third vector which points perpendicularly. There's such thing as a triple product, which combines the dot and the cross product, and that also can be given through the determinant of a matrix, combining the three components in the rows of that determinant matrix. A position vector is something very valuable in physics. It's usually radially described, so you'll see R as the vector describing it, and the components x, y, z. So finding the magnitude of that vector is very familiar, and we can create a unit vector by taking that vector and dividing it by its own length. That'll give us a vector in that direction, but having a length of 1. That's very useful in physics problems. You can also do this two-dimensionally with just x, y, and this vector could be rotated through the plane of an angle, let's say theta, using matrix notation. If you took xy to be the vector of a column matrix 2 by 1 and multiplied this by something called the rotation matrix, you would see that the resulting x bar, y bar coordinates would be rotated by the angle theta. The entire frame would be rotated, the coordinate system would be rotated, and we get a series of equations, a system of equations that describe this. Transformations in 3 dimensions tend to look a little bit more complicated because you're adding more direction. So these matrix multiplications are really summations of products of things, elements of the matrix in the coefficients, and that gives us some new values to the XYZ components. In the next video, we talk about a little differential vector calculus. Stay tuned.